Hi class, we are going to cover the last section before our last midterm. Today we're going to study applications of eigenvalues and eigenvectors. So we're going to use these things to solve systems of differential equations. Okay, so you should have studied differential equations in Calculus 2 and in Calculus 3. So this should be your first exposure to systems of differential equations, unless you have taken a differential equations course before you took your linear algebra course. Okay, so we're not going to get super deep into DEs, but I'm sure that you're probably a little rusty on how these things work. So we'll do a quick overview of what differential equations are and how they work and what they're used for, and some of the verbiage that we're going to use. And then we're going to get started into a couple of examples. Okay, so differential equations are exactly that. They are equations that contain derivatives, right? So if you have an equation that has a first derivative, a second derivative, or higher, it is a differential equation. We use them to model things that change over time. Derivatives are used to model rates of change, right? That's what a derivative is. It's an instantaneous rate of change. So anything that changes over time or period that just changes, we can model with derivatives, right? And if we can model it with derivatives, then we can model it with a differential equation, right? So an example of some of those things are traffic, right? As traffic flows, we live in the Bay Area. We know that traffic gets worse at certain parts of the day and even better during other parts of the day or during pandemics. So we can model traffic flow with D.E.s. And when we say traffic flow, we don't mean necessarily just cars on the road. We can use the same equations that model cars on the road to model things like behavior in ants and termites as they travel from one place to another in a line of traffic. Okay, heat flow. Heat flow is extremely important. If things get too hot, they tend to break or warp. So heat flow is a very important sort of equation that we use to model. Heat flow can also be used to model things like water flow. So there's lots of anything that flows can be modeled with differential equations. Weather can be modeled with differential equations. The equation for weather is very similar to the equation for traffic, actually. Motion of celestial bodies. So how the Earth changes position over time, how the moon changes its position in relation to the Earth or relation to the sun over time, and so forth and so forth. So our entire picture of our solar system is modeled with differential equations. Okay, obviously if we want to take a person from the Earth and send them to the moon or what have you, rocket science, for lack of a better term, is modeled with differential equations as well. Okay, population growth. So this should be important to us because we think of population growth normally as people or animals, but we can also think of population growth as smaller things like bacteria, viruses, right? Something that's important for us right now. So we can model population growth of anything using differential equations. We can model our finances. Also, the stock market is modeled using differential equations, etc. Right? There's lots and lots of applications of differential equations. So it's a very, very important field of study. Okay, so let's talk about some of the classifications of differential equations. So there's lots of different classifications. So we can classify a DE in terms of many of its characteristics. Some of those that we use are their order. Okay, the order is similar to its degree, right? So for a polynomial, I might say I have a third degree polynomial. For a differential equation, it doesn't make sense to talk about its degree because degree is the highest power. So we talk about its order. So if I have a third derivative in my equation and that's the highest derivative, it is a third order differential equation. Okay, so the highest order is similar to how we use power for polynomials. Okay, homogeneity, right? I can talk about my differential equation being homogeneous or non-homogeneous. So I can have a second order homogeneous differential equation. Okay, so all these terms kind of get linked together when we start to talk about them. Okay, its type, an ODE versus a PDE. An ODE is an ordinary differential equation. These are things that have very standard derivatives. First derivative, second derivative, 10th derivative kind of deals, right? A PDE is a partial differential equation. This will have partial derivatives, okay? So partial derivatives, PDEs are much more complex and difficult to solve. ODEs are sort of your first exposure to differential equations. The course that you take at community college would generally be your first course in ODEs. There's several levels of things involved. So right now we're going to be focusing on ODEs, ordinary differential equations, and then the conditions present. So an IVP versus a BVP. IVP stands for initial value problem. There are some initial conditions that are set. My function, my solution has to satisfy these conditions before I can say that it's a true solution. A boundary value problem means that there are conditions that are set at the end of my function. Okay, so you can think about it like if I'm talking about, let's just take heat flow because that's very important. If I have a solid bar, maybe the initial temperature of my bar before I start to model heat flow has to be at a certain temperature. That's an initial condition. Okay. A boundary value problem for that same problem would say that after a certain amount of time, I need my bar to be this temperature, or at the other end of my bar, if I'm modeling the flow of heat through it, maybe at the other end of my bar, I need that part to be at a certain fixed temperature as well. Okay, so maybe it's impossible to have a BVP. For instance, maybe my initial value for a bar is that it is 1,000,000 degrees and the bar is only 2 inches long, and at the other end of the bar it needs to be 0 degrees. That can be an impossibility, so BVPs might not have an actual solution to them. Your IVPs though, your initial value problems, they should always have a solution. Okay, almost always have a solution. So we're going to focus on the IVP part for today. When you take a differential equations class, you'll consider kind of both of these things, right? And then the linearity, right? Linear versus nonlinear. So I might say that I have a second order linear non-homogeneous ODE, right? So these things can all be put together again to classify the type of differential equation that we're talking about. The different types of DEs all have different types of methods for solving them. Okay, so the way I solve a linear versus a nonlinear are different. The way I solve homogeneous versus non-homogeneous are different. The different orders have different methods. The ODEs versus PDEs, they all have different methods. So this is a very robust sort of deep topic to talk about. So we're just going to skim the surface to try to get an idea of how to use linear algebra to make these things easier to work with. Okay, so the first thing we want to talk about is what these things actually look like. Okay, so let's talk about the easiest case. Obviously would be a first order DE. Okay, we would not want to start off with like a 10th order DE. We start just like with algebra. We start off with linear equations before we do quadratics or higher order polynomials, right? So let's start with the first order differential equation. So these have only a single derivative. Okay, so a derivative equals some function of y. Okay, a here is a constant, right? So here what I'm saying is that the derivative of my function is going to be a constant multiple of the function that I'm taking the derivative of. Okay, so here y is my function. It's a function in x or t or whatever it is that I'm working with. A obviously here is going to be a constant then. So if I take my function and I take its derivative will be equal to a constant multiple of the original function. And that's what we're looking at for our first order DEs. Okay, So instead of going through the process of solving these things right now, right, what we're going to do is we're just going to assume that my function is an exponential function. Okay, a constant multiple of e raised to the power of x, where x is also multiplied by some constant. Okay, so if I take the derivative of this, the a comes down and I get ac e to the ax, and if you notice, this ac is a constant times a constant. So what do I get when I take the derivative of this? I get a constant times my original function. Okay, ac is a constant. I'll just rename it a. It's easy. So this c is not going away. I'm just calling ac a new constant. I'm just going to call it a again. What is y? Y is e to the ax, right? I could have easily just called this a new name, but it's generally what we do in DEs is we just, if it's a constant, it's a constant. It doesn't matter. I just write it as a constant, right? So AC is just a new constant. I'll call that new constant A. So I got y prime is a constant times my original function. Okay. So what does that mean? That means that things that look like this are solutions to our first order differential equation. All right. So let's move on to the next thing. So now that we have an idea of what the solutions look like, let's talk about these initial conditions. Okay, these are important. Generally what happens is, if you notice here, let's say this is y prime equals 3y, for instance. Okay, then my solution here would be y equals some constant, right, times e to the 3x. This constant would be unknown, and since this constant is unknown, that means I have an infinite number of solutions, right? Because this could be a 1, this could be a 2, this could be 3, this could be 1/2, this could be pi. It could be all different, an infinite choice of values. So there's infinite solutions for this equation, okay? Even when there's a number here, even if this is, again, like 3y. So what happens is our initial values, they allow us to pinpoint a single solution. So if I have an initial condition, say I need my equation to pass through 5 when I'm at x equals 0, I can narrow it down to a single solution instead of a family of solutions. So initial values, initial conditions are very important because they allow us to have, instead of a general solution, a single solution, right? So IVPs are very, very, very common, especially if I'm trying to answer a very specific type of question. If I don't have a specific question, I just want to know what the solutions to something kind of looks like, then a family of solutions is fine. But when I need to know an exact solution for an exact problem, that's when an IVP comes into play. So that's what we're going to do right now, is we're going to look at initial conditions. Okay, so our differential equation may have some starting values that have to be satisfied by this solution that we're trying to find. Okay, so let's just do an example of this. We're not going to solve it from scratch, or I guess we're ever going to solve it from scratch. So again, these are called IVPs, right? If it has initial conditions, it's an initial value problem. So here's our example. Say that y equals 3 when x is 0, and that this is our problem. This is our equation that we want to solve. So I want to solve y prime equals 4y, and I need it to satisfy the condition that I have an output of 3 when I am at 0, right? So this is my initial condition. So when I'm just starting out, right, I need to have an output of 3, or you can think about it as I need to have a y-intercept of 3, right? So our solution here is y equals some constant multiple of e to the 4x, because we saw what the solutions to this look like, right? So the solutions are just whatever this constant value was raised to the e times x. But the c is unknown, right? Right now I have a family of solutions, but when I apply my initial condition, I can whittle it down to a single solution, right? So this is my condition. When I plug in 0 to my equation, my solution here, right, I should get out 3. So y of 0 is 3. Tells me that I get out 3 for y, right, when I plug in 0. So then e to the 0 is 1. That gives me 3 equals c. That means that the solution to this IVP here is y equals 3 times e to the 4x. Okay, and that's the importance of an IVP, right? An IVP, again, takes us from a family of solutions to a single solution for our situation. All right, so now that we have an idea of what a differential equation is, what, especially the linear ones, what their solutions look like, what some initial conditions mean for us and our solutions, we can start to take a look at the linear algebra, right? Basically, what do a system of linear D.E.s look like? Because remember, if we have a bunch of equations that work together, that creates a system, we can turn it into matrices, right? So obviously, for linear algebra, I need more than just one equation. So let's look at a first order system. Okay, so multiple differentials where the highest derivative that shows up is the first derivative. Okay, so these will have this form. So I have the first DE. Okay, so y1 prime will be some coefficient times my first function plus some other coefficient times my second function. So each of these yi's are a function and they work together in a system. So my second derivative is also some sort of linear combination of those functions all the way down until I'm taking the derivative of all of those functions. Okay, here each of these yi's is a function in x and is differentiable. If it's not differentiable, then obviously it can't show up in a differential equation, right? So each of these, so y1 is a function, y2 is a function, y3 is a function, all the way up. And in my system, I need to have those derivatives for each of those functions. Okay, so this is what my system will look like. So we can rewrite this in a matrix equation where I'm taking the coefficients here and I'm turning them into a matrix, which I call A. I have a y vector, which is y1, y2, all the way to yn, and that will equal my derivative vector, right? Where I'm taking the derivative of all of these y's, and that is my vector. So I can write this as a matrix equation, which we know how to solve. Okay, we're actually not going to solve this in the general way. We're going to use, obviously, eigenvalues and eigenvectors to do this. Okay, so if I have a coefficient matrix times a vector u, and that's equal to lambda times u, so they're the same thing, then y equals e to lambda t times u is a solution to this system of differential equations. Okay, so again, this u is an eigenvector. This lambda is its eigenvalue, right? So my solutions are made up of eigenvalues in the place of where the a's used to be. And since I'm going to have a bunch of those, I'm multiplying them times their eigenvectors. Okay, so I'm not solving this system in the way that we did with regular matrix algebra, where I'm taking the inverse of A and applying it to both sides, because this is not a straightforward algebra equation. This is a DE, right? So now I have to use these eigenvalues and eigenvectors. Okay, so here's another theorem. If my coefficient matrix is diagonalizable and it has eigenvalues of lambda 1, lambda 2 up to lambda n, and each of these eigenvalues have an associated eigenvector, okay, then my general solution to this equation is going to be a linear combination of those solutions, right? So a constant multiple of this solution times its associated eigenvector plus a constant multiple of this solution times its eigenvector, and so forth, right? So my solution to the system is a linear combination of these solutions. Okay. Next theorem, if A is a real matrix that has complex eigenvalues of the form lambda is alpha plus beta I, and it has an associated eigenvector, which we'll call u, then the solutions work in the same way that they do when we were taking eigenvalues and eigenvectors of that were complex. Okay, so we're combining the last two sections together, the diagonalization and the complex eigenvalues and eigenvectors, and we're putting them together to form our solution. So my solution is e to the alpha form of x cosine times the beta form of the positive, right? We're not taking the negative, we're using the positive here. If we use the negative, we have to kind of switch everything around. So we're using the positive form times the real part of u minus sine times beta and the imaginary part of the eigenvector. And then the second half is the same thing, but we're switching the pieces, right? So this should look familiar to you. Cosine, sine, sine, cosine, right? We had this when we're diagonalizing the complex vectors, but we had it differently. This was actually backwards. This one was negative and this one was positive. So it really just has to do with diagonalizing your complex values. But we're not going to worry about the signs because remember I took positive and then I switched these things out. We don't have to worry about that right now because it really just takes care of itself. So we'll just plug them in to where they need to go in this form. There is some more advanced methods where we can use a lot more matrices that I'm not going to really go over with you. You will see those again whenever you take your next differential equations course, or I'm sorry, whenever you take your next linear algebra course, or really when you take a differential equations course, a higher order differential course, I should say, you'll go over much more methods that you need to apply matrices in linear algebra to. Okay, so I'll leave that for a later time because we're going to get into things that are a little more advanced than we need, so don't worry about that. Okay, so let's start with an example. Okay, so let's find the general solution for the following system. Okay, so three different functions. The derivative of the first function is equal to the second function minus the third function. The derivative of the second function is the first function plus the third function. And the derivative of the third function is the first function minus the second function plus 2 times the third function. Okay, so this is our system. So obviously the derivative of y1 is dependent on the other two functions. The derivative of y2 is dependent on the other functions. And the derivative of y3 is dependent on the other functions as well as itself, right? So it's in a system because they're all involved in each other's equations. They're all in each other's business, right? So what we're going to do is exactly how we outlined it before. We need to look at this coefficient matrix. Okay, so we're going to turn this into a matrix equation, right? We're going to turn this into this matrix equation. All right, so I have my coefficients 0, 1, negative 1, 1, 0, 1, 1, minus 1, 2. Right, I'm going to multiply that times my variable vector. Right, so the things that I'm using here as variables are the functions themselves, y1, y2, y3. So if I multiply this times this, I get my first function, right? And that should equal y1. When I take this times this, I'll get the second equation, and that will equal y2 prime. When I take the last one times this, I will get my y3 prime. Okay? So I set it up as an equation, and so now I'm only going to work with the coefficient matrix, right? This is what I'm going to work on in order to solve this problem. So using the methods that we have, we know we need to look at the eigenvalues and eigenvectors. So we'll start off with find the characteristic polynomial, right? There's lots of ways to do this. There's a bunch of zeros. You can use cofactor expansion. You guys know that I like to use the repeated columns method. So that's what I'm going to do. So remember, you are subtracting it's lambda it's lambda I minus a, right? So the lambdas are here, and then I'm subtracting my A matrix. So all of these things that are not on the diagonal change signs, and then if this is a plus, it turns into a minus 2, and the lambdas are on the diagonal. Okay, so when I go through, so remember I go this way, okay, and multiply. So I'm going to get lambda squared times lambda minus 2 plus, so -1 times -1 times -1, so that'll be a -1. This will be another -1, and then I'll go this way, and I'm going to subtract a, this will give me a negative lambda. So that'll be plus lambda, and this will be a minus lambda minus 2. Okay, so lambda squared times lambda minus 2. The next one gives me basically -3 cubed, so plus a -1. This is 1 negative, and I'm adding it to stuff, so that's another minus. This is a minus and a plus times lambda, so minus a minus gives me a plus. Same thing here, minus a minus gives me a plus. These are two negatives, and I'm subtracting them, so I'm still getting a negative times lambda minus 2. Remember to put the parentheses here, you guys. Okay, don't get sloppy. If you don't put a parentheses here, you will forget to distribute this negative, and if you forget to distribute this negative, you will have a completely different set of eigenvalues. Okay, if you have a completely different set of eigenvalues, that means you have a completely different set of eigenvectors, which means you might not have an invertible P matrix. Everything is just going to go all haywire, right? So just make sure you're staying organized and going slow. Okay, so let's try to start to work this down. So if you notice, I'll have a -2. When I do this, I'll have a +2, right? I'll also have a negative lambda and a positive lambda, so that'll go away. So I'll really have this expansion plus lambda. So this will be a lambda cubed minus 2 lambda squared plus the 1 lambda that's left over. Okay, so that's nice. It simplifies very easily. Now I have a common factor of lambda that I can pull out. And this is factorable, right? It factors very, very nicely. You don't have to do your rational zeros theorem or synthetic division or any crazy thing or quadratic formula. This factors nicely to lambda times lambda minus 1 squared. Okay, so we have our zeros. My zeros, my characteristic polynomial equaling 0 implies that lambda is 0 and 1 with a algebraic multiplicity of 2. So I have 2 1s here. So now I need to find my eigenvectors. Okay, so let's start with 0 because there's only 1 there. It'll be the easier one to work. It is the easier one to work with, right? So remember, I'm plugging in 0 here. So my matrix will be 0, -1, 1, -1, 0, -1, -1, 1, and -2, right? I'm just plugging in 0 for lambda to my characteristic polynomial matrix. So when I simplify this down, I can throw it in my calculator, do reduced row echelon form. I could do it by hand. It's not super difficult, right? We all know or should know how to do this by hand by now, so that's great, right? But we can throw it in our calculator, and we should get it down to this form. So if you notice, my free variable is x3, okay? x2 is equal to x3, x1 is equal to negative x3, right? So if x3 is 1, that means that I have x1 is -1, okay? If x3 is 1, then that means x2 is also 1. So that gives me my first vector, okay? -1, 1, and 1 when I choose x3 to equal 1, okay? If this is 1, x2 is 1. If this is 1, x1 is -1, right? So that's my first eigenvector, okay? Hopefully you guys are writing this down because now I'm going to switch to a clean screen. So you'll need to remember what this is. So make sure you have it readily available to you because we're going to plug in 1 for all of these parts. So 1, -1, 1, -1, 1, -1, -1, 1, and then this is 1 minus 2, so it'll be a -1 there as well. Okay. So we have our matrix here. Okay. So again, I want to solve this down as much as I can. So I throw it into my calculator. And now you notice that we have 2 free variables, x3 and x2. So that should give me 2 vectors out. Okay, 2 vectors. So if x3 is 1, okay, then I will have basically 1, 0, and I'll have -1, 0, 1, okay, when x3 is 1. And if I choose x2 to be 1, then I will have 1, 1, 0, right? So again, since this relies on two different free variables, it gives me two different selections. Okay, so if this is 1, then I get 1, 1, 0. If x3 is 1, then I get negative 1, 0, 1. Okay, so those are my two eigenvectors. So I have algebraic multiplicity 2 and geometric multiplicity 2. Okay, now if I did not, if this only gave me out one vector, one eigenvector, I would not be able to diagonalize my matrix. If I can't diagonalize my matrix, there's things that we can do that we're not going to go over. Again, that would be left for a differential equations course. But at this point in time, we would say that I can't diagonalize it. I don't have a solution. Okay. There are ways around that, but we don't go over that in this course. So my solutions then, for the first one, where my first eigenvalue is 0, this is what my solution looks like. For these two, where I have multiplicity 1, okay, these are what my eigenvectors look like. These are what my solutions look like. Okay. So my general solution then is the addition of these three solutions, right? So that's the linear combination. Okay, my superposition principle is what it's called. So my solution is C1 times this vector, because e to the 0, no matter what value of x I get, is just a constant. So I have C1 constant, negative and positives for the different cases. I have e to the x because it's a common term for this solution. One is times the constant C2, the other times the constant C3, so I can pull out the e to the x, and I can put these two together because I'm just adding them, right? So this is what I would call my solution. If I want to, I can write out each individual function, although it's not necessary. Generally, we would leave it like this as my solution. But if I want to write each one out, this is what y1 looks like: negative C1 plus C2 e to the x minus C3 e to the x. Okay, and for y2, this is what my solution looks like, and for y3, this is what my solution looks like. Okay, and so that's what it looks like if we write out each function. So let's do one more example. This one we're going to step it up a little bit, right? So we will look at a case where we have complex eigenvalues and eigenvectors and initial conditions, right? So if you notice, these are each families of functions. Oh, I thought I fixed this. This should be subscript 3, not C3 e to the x. Okay, sorry about that. So we should have so here this is a family of solutions. C1, C2, C3, they can be any value. There's infinite solutions. As long as the solutions look like this, they satisfy our differential equation. Okay, so if I put some initial conditions on it, I could solve for C1, C2, and C3 explicitly and have actual values. So this next example is going to be an IVP, initial value problem, and we're going to look at what it looks like when we have complex eigenvalues and eigenvectors. Okay, so everything works the same. There's nothing different than what we've been doing before, although we're not diagonalizing. So we're just solving for those eigenvectors and those eigenvalues, and then we're using those to finish this up. There is a way to solve these by diagonalization, but again, that's left for an actual differential equations course, a higher level course at that. Okay, so let's start our next example. Okay, so I want to find the solution for the following IVP. Okay, initial value problem. Remember, IVP, initial value problem. So initial conditions. I have this system of equations with the following conditions on each of the functions that I'm looking at, right? So y1 looks like this, y2 prime looks like this, y3 prime looks like this, and if you notice my initial value problems, they all have to be at the same initial value. y1 has to be at 0, y2 has to be at 0, y3 has to be at 0. Now, it does not have to be 0. I could say I need all of these to be defined at these points at maybe x equals 1 or x equals -5. Right? We generally just choose 0 because it's nice, things disappear, makes the math a little easier. but it does not have to be at 0. Okay, it could be at a different value and still be an IVP. Okay, so let's get started. So again, what do? I start off by making a coefficient matrix, right? So I turn this into a 3x3 matrix, right? Times my y vector will be the y prime vector. Okay, I don't have to expand the whole thing. I really just need my coefficient matrix, because once I have that, I can use it to find my characteristic polynomial. Now, if this was 0, then I would have a diagonal matrix. I'm sorry, a triangular matrix, and then finding the eigenvalues from that. It's super easy, but there's a 2 here. So I can do cofactor expansion if I wanted to, because I have 0, 0, 0. So I could just choose this one and delete this row and this column, and then find this subdeterminant, and I'd have my cofactor expansion. I think that I went ahead and I just did my 3x3 anyways. Okay, so I just repeated the 2 rows. What's nice about that is that I still have my diagonal. This will be 0, this will be 0, this will be 0, this will be 0, and then I'll have the other part, right? So there's really only 2 kind of parts in play here. One diagonal in the positive direction, one diagonal in the negative direction, because those zeros take care of everything. So regardless of which method you use, having a bunch of zeros makes things really nice, right? So what does that look like? I'm going to have lambda squared minus 9, right? Because it's a difference of squares, times lambda plus 1. And then this one will be a negative 10, so positive, times lambda plus 1. So I have this, okay? Now you could expand this out and expand this out and combine all my like terms, or again, right, use the methods that you know. This is algebra. I have a common factor here of lambda plus 1. So let's just pull that out, and I'm left with lambda squared minus 9 plus 10, all of that being multiplied by this common factor. So that makes this really nice. Lambda squared plus 1, which gives me a complex solution and a real solution. Okay, minus 1 and plus or minus I, right? So again, remember, I'm not using both of these. I only need one. Okay, I use the positive one. The positive one will give me both the solutions I need. And then I have this negative one from here. So I'm only using one of these values. Okay, so use lambda 1 is negative 1. If I plug that back into my lambda I minus A matrix, okay, here, then I get the following. So if you notice, I have a row of zeros, which is good because that tells me that it is dependent, right, which I need. So if I simplify this down, I get the following. Okay, now you might be saying, well, what the hell? Everything is 0. x1 is 0, x2 is 0. That means that this vector is a 0 vector. If I have a 0 vector, that makes everything go all crazy. It's not going to work. Wrong, right? I have a free variable here. There's nothing here that says that x3 is 0. Okay, x1 is 0, x2 is 0. So this is a free variable. So I'm going to have the vector 0, 0, and 1. Okay, just because you have all zeros does not mean everything is 0. There is still a free variable here. Okay, so this is my eigenvector. Okay, very important, because if you have all zeros, you're not going to find the solution. Okay, we always want a non-trivial solution. We never want our vectors to be all zeros. If we did, we screwed up somewhere. Okay, so now I'm choosing lambda 2 equals I. And that's going to give me this matrix when I plug it back in into my lambda I minus A matrix. And we want to solve this down. Okay, now I went ahead and I just did it by hand. Sorry guys, I apologize now. I really just didn't feel like typing it up. It's a very long process to type all of these things up. Again, this isn't used in Word. I literally have to code the whole thing out and then compile it. So use this as an exercise as practice. Go ahead and simplify this down into reduced row echelon form yourself, and just get some practice in getting it into the right form. Okay, again, if you use your calculator, you're gonna get some crazy answers, and that's not what I want. Okay, I'm always gonna ask you for exact values. So if you give me some value with a bunch of decimal places, I'm not really gonna score you very well on that. Okay, so again, also, now that we're on the topic, your WebAssign is probably not going to take those answers either. It's going to want exact value, right? So get into the habit of working these down by hand, right? So if you work it down by hand, you should get this, okay? So go ahead and pause it now and take some time and just go ahead and do this on the side, and you have the answer for what it is. Just use this as practice to practice getting into the correct solution, right? The correct form. Okay, so pause it, do some work, right? Reduce this by hand and see if you can get to here, because this is the right answer. Okay, so hopefully you did that, and now you're at your back, right? Obviously x3 is a free variable, right? So I know what x2 is, I know what x1 is, so I can move these over to the other side of the equal sign, right? So now everything is positive instead of being negative, which is great. X3 is the free variable, so that gives me my two vectors, the real part and the imaginary part. Right, so x2 looks like this. When I separate it out, this is my real part. Okay, anything that does not have an I is real. All the stuff with the I is imaginary. So the real part are these three, and the imaginary are these two and 0. Okay, so these are my two vectors that I'm going to use, the real part and the imaginary part. So now I have all of my pieces, I have all my eigenvalues and their associated eigenvectors. So I need to throw them all together to form my solution. Okay, so before we start, just remember, right, for this eigenvector that I have, eigenvalue, I'm sorry, my alpha is 0 and my beta is 1. Okay, because if we go all the way back, again, look in your notes. Okay, let's go all the way back real quick. Just to remind you, we gotta go way back. Okay, this is what it looks like for the complex part. Okay, so we have a real solution, so we're gonna have this in our solution. We also have a complex solution, so we're gonna have two parts. Okay, and again, remember, this is what we got when we did our diagonalization. Okay, when we're going through the diagonal forms in on the last video, right? The cosine, sine, sine, cosine. The only difference was that this was positive and this was negative. Okay, but again, I told you don't worry about that. It all works out. Okay, so what we're gonna do, okay, is we're gonna plug our alpha, which was 0, so this will go away. Our beta was 1, so, and we have our real part and our imaginary part. So when we come back here, okay, all right, so alpha is 0, beta is 1, so plug all this into our solution, and this is what we have. Okay, C1 times e to the negative x, because my first one was -1, and this is the eigenvector that goes with it, right? For these two, for x2, for my imaginary one, there is no e here because alpha is 0. Okay, beta is 1, so it's just cosine x, sine x, sine x, cosine x. And look, I very nicely put it in the order, top and bottom, right? So cosine and sine, sine and cosine. So it looks like this. Okay, the real part, imaginary part, real part, imaginary part, right? So I really just threw everything in where it's supposed to go. Okay, so the next thing that we're going to do then is we are going to simplify this. Okay, but before we simplify this, we're going to apply our initial conditions. So remember, we had initial conditions. I need to use those to find C1, C2, and C3. Okay, so here all I did was just repeat this. I didn't move anything. I just brought it down again so we can work on it. Okay, right, this is the same as that, right? It's just a lot, so I don't want us to get lost. So my first condition is that y1 of 0 equals 1, so I'll apply that. Okay, so again, I'm going through the top vector. Okay, everything on the top is the first one. So C1 e to the negative x times 0, so I don't have to worry about that. C2 times 4/13 cosine x. C3 6/13 cosine x, and then the same thing here, right? So this is the first function. Remember, the first function is the top entry on these matrices. So this is what it's going to look like. Okay, if I plug everything in, it's going to look like this. And so cosine of 0 is 1, sine of 0 is 0, so this whole thing will go away, and I'm left with this equaling 1. Okay, so I do that again for y2 of 0 being negative 1. I go through the exact same process. Okay, I didn't write it out this time, I just wrote the results, so I'll give you guys a second. But again, this sine parts all go away, this part all goes away, and I'm just left with these two cosine parts, the C2 9/13 and C3 7/13, because cosine of 0 is 1. So I have these parts equal negative 1. And then my last condition is that y3 of 0 is 2. So this one actually shows up. That's the only time this one shows up. Of 0, so again, this whole part goes away. I don't have to worry about that. And if you notice here, this cosine only has one C2. So I should have C1. This goes away because I'm plugging in 0. So I have a C1 plus C2 is 2. Okay, so this is my system of equations now that I need to solve. So again, I'm using pretty much everything that we've learned in these equations, right? So eigenvalues, eigenvectors, we're talking about vector spaces to a certain point, right? Linear independence, span, linear combinations, everything we've learned so far is showing up right now, right? So again, that's the way linear algebra works. Everything that we've used just keeps on compiling and compiling and compiling. And so once we're done with this eigenvalue, eigenvector section, we're going to use all this stuff again to talk about even more abstract concepts in the next chapters after your midterm, right? So let's solve this system. Let's put it into a matrix. Okay, so C1 is missing for most of these. Okay, C2, C3, right? I have my systems here. You can do reduced row echelon form if you want to, but you should know by now that really inverses are much easier. So if I multiply this by its inverse on this side, I just multiply this by that same inverse on the left side. Okay, right? So I take the inverse on the left side times my vector, and I'll get my solution. I feel like that's the easiest thing to do. I don't know, I just like inverses. They're much easier to work with. Okay, so then this is my solution. Okay, so I have this is C1, C2, and C3. So then what I'm going to do is I'm going to go ahead and throw this back into my solution, right? So I'm going to come up here. C1, C2, and C3 are going to be replaced. Oops, sorry guys. C1, C2, and C3 are going to be replaced by the values that I have for them. Okay, so if I come back, and this is me just going through and plugging them in. Okay, I literally just plugged them into where they had to go. I haven't done anything yet. This is not okay as a solution though. There's still a lot of work to do. If you see 13 cancels a lot here, 13 cancels here, 13 cancels. There's a lot of extra stuff going on here. You always want to simplify things down as much as possible. So let's go ahead and start to simplify. So I have my cosine x's here. I simplified my two matrices. Okay, so I have cosine times these two things, sine times, now this has been simplified. I can add these together. I have distributed the 13s over 2 into everything, so things have canceled out. A little bit nicer looking. Okay, so I have this matrix. I can add these together. I can add these together, and I can get a much simpler answer. Okay, again, don't give me this. I don't want that. Your website is not going to like that either. Right? Simplify it down. It's a math class. Remember that the goal of math is not to give something complicated to read, but to simplify it for them. and give them the results, right? That's what we're preparing you to do. If you're an engineer and you give this to your boss, he's like, what the hell is this, right? But if you could simplify it down as easy and simple to look at as possible, it's easier for people to digest and understand, give you some raises, those kinds of things, right? So this is my answer, okay? I simplified my vectors into one single vector. My e to the x is just this one portion here. So what happened is that it looks like this vector disappeared. Okay, so this vector here should still be here because this is not being added to all of these terms, only to the last portion. So when I compiled this together, it must have got mixed up. So I'll fix that in the write-up. But this should be 001 vector here. Okay, so apologies for that mix-up. Everything else looked pretty good though. Not too many mistakes in the write-up, so that's nice. And here is your classwork. Okay, so again, this is going to be due by the end of the day. Simplify it as much as possible, show all of your work, and I will post something, or by the time you get this, actually something will be posted for you to work on for review material for your midterm that is coming up due on next Tuesday.